Hey, morning. So it is May 26th. This is day 5, right? So today we're going to be doing chapters 4 and 5 in the text. We're going to roll through kind of quickly. So I got some videos that I'm going to put on YouTube along with this one that are, as I said earlier, people that make professional videos do a far better job than I of managing all this. So for some of the basics, I'm going to post these videos on atom structure and nuclear chemistry. Okay, so that's chapters 4 and 5. Let's jump in. We roll back to the top. So chapter 4, we're talking about atoms, right? Atoms and elements. So we said that elements are the simplest single structure that everything can be broken down into. Well, those elements consist of atoms, all right? And atoms are the smallest particle that cannot be broken down anymore. At least that used to be true. We can kind of break them down. We'll talk about that when we get to nuclear chemistry. But okay, so the elements, are represented by these letters. They're called chemical symbols, and they are named for various reasons. Some of them are based on who discovered them. The Latin words for the materials when they were first discovered, stuff like that. So the chemical symbols are these letters that represent, like cadmium is represented by CD, right? Capital C, lowercase d. Some of them have one letter symbols. They're more commonly used in chemistry. Carbon, sulfur, nitrogen, hydrogen, for example. Yep, so you can find all these on the periodic table. The periodic tables is something that lists all the elements out based on structure and energy, which we'll start talking about here soon. So let me bring up a periodic table for you to see more closely. I'd recommend keeping one of these with you, handy, either on the internet or in a hard copy, so you can reference it when you're doing the questions. This is a good periodic table. You see here it tells you the atomic numbers here, symbols here, atomic weight, which we'll get to in just a second. All right, let's go over the periodic table. I just want to mention quickly that it's listed, and the book goes over this in columns and rows, right? So these columns have numbers above them that will tell you the group number. Okay, so everything in hydrogen and below hydrogen is in group 1, and you'll see this 1A here. All right, beryllium and everything below is in group 2. I want you to skip these transition metals, and the book kind of mentions it, but so these earlier elements were discovered and categorized, and then as we found these transition metals, we found that they went in between these two sections, so we had to fill it in, and that's why you'll see the B on the back end. This is group 3B, and 4, 5, so on. This is 3A. Okay, so 1, 2, skip over here, 3, 4, 5, 6, 7, 8. Okay, now these here on the far right, they're called noble gases. Okay, they're real stable, and you won't see them connected to other atoms in most cases. There are a few exceptions, but these kind of stand alone and are important in their own right. So yeah, periodic table, this will tell you all the elements. It'll tell you all the information concerning mass and atomic number. And it's also categorized in their characteristics. Okay, so everything here in the red is alkali metal, right? And they have similar characteristics with each other. All right, that's another way these are classified. So all these are alkaline earth metals, transition metals, right? We have metalloids here, which are something in between these and these physically, right? They have qualities and characteristics of both metals and non-metals. Okay, so that's why we call these metalloids. The actinides, and then we said the noble gases. Okay, these are radioactive elements down here, and they're not as commonly used. The lanthanides and reactive nonmetals. All right. So this is just some categories and classifications for the elements. This is the periodic table. You'll use that very often. Okay, let's go back to the text, see where we're at here. Okay, and this is where I was talking about group. These are the transition elements in between that original group and this second group of nonmetals right here. Okay. Let's see, talks about each of the groups. That's good. Okay, so now we're going to break down the structure of the atom. As I said, I think the video goes into some good detail about this. I'll just quickly mention Dalton's atomic theory, right? I'd keep this, I'd kind of memorize this, or make sure you understand what's going on. All matter is made up of tiny particles called atoms. All atoms of a given element are the same and different from atoms of other elements. All right, we'll talk about that in just a second. Atoms of two or more different elements combine to form compounds. A particular compound is always made up of the same kinds of atoms and always has the same number of each kind of atom. So we talked about compounds, right? Water, acetone, these different substances that are made up of multiple elements, all right? Chemical reaction involves a rearrangement, separation, combination of atoms. And we're going to start writing out chemical equations soon. So that's going to be important to know how the atoms are moving between bonds or in a reaction. Okay? Subatomic particles, excuse me. Proton, neutron, electron. Most of you should have covered this, throughout your childhood education. Something that you may not have seen is this atomic mass unit, which is the way that we represent weight or mass for atoms. They're so tiny and so small that we have to use these scientific notations and to be able to represent the weight of an atom, because it's so very small. And you'll see here the electron is even smaller than the proton and neutron. So when we talk about mass number and atomic mass, atomic number, okay, these are all referencing the number of protons or neutrons in the atom. So the atomic number is just the number of protons in the atom. The mass number is the protons plus the neutrons, okay, because there can be different number of neutrons in the same element, if that makes any sense. Let's where's an example? Magnesium, I think, is an example. Oh yeah, it'll go into the practice, examples when you get down to 4.5 isotopes atomic mass, okay? So an isotope, we just said that the same atom, same type of atom, same type of element can have different numbers of neutrons. So the varying structures are called isotopes. They are isotopes of each other. So magnesium has 3 isotopes, magnesium 24, 25, and 26. And it's all based on the number of neutrons that the atom has, okay? So that's pretty straightforward. It's just addition. You see here, this kind of tells you, if you're looking on the periodic table and it's listed in this way, you'll be able to know how many protons, how many neutrons, what the mass number is of the element you're looking at. So Important to have that periodic table, and here goes a good example here. Chlorine, 17 atomic number, 35 atomic mass. So keep that in mind. That's going to be in your practice. Okay, electron energy levels. Okay, let's talk about energy. So the energy that comes from atoms and elements is essentially held in the electron, and that's because of a couple things. Because of its position to the rest of the atom. Okay, an electron has a negative charge. The proton in the middle has a positive charge, and so we know that opposites like to attract, and they'll pull on each other. Okay, and that resistance or attraction will create some energy. All right, and now the energy that is released can be measured in several different ways. Okay, we talked about heat, right? Kinetic energy is the molecules moving around. Potential energy is the energy that's held in a bond. But there's also electromagnetic energy. Okay, and that's what this is here. This is a scale of electromagnetic energy. So we see it has heat listed here. Visible light is also a form of electromagnetic energy. X-rays, power lines, FM radio, television. So all these ways that we send signals or whatever, this is a form of energy that we can read and measure and interpret. All right. The one, like I said, you're most common familiar with is visible light. Right? When you see light reflecting off a surface, that is electromagnetic radiation bouncing off of that surface, hitting your eye, and being interpreted as an image. Okay? So this is really cool. It can also get very complex as well. So I won't go into much detail, but you should know that the differences in the energy have to do with the differences in their wavelengths. So you'll see this scale here in your text. Well, that is talking about the different wavelength size and also the different frequency. So as the wavelength gets larger, right? So this will be 10 to the 5 will be the largest wavelength on this scale. 10 to the negative 11th would be the smallest wavelength. So as the wavelength gets larger, the energy gets less harmful. Okay, so high energy, I want you to think about gamma rays, X-rays being very high energy, and FM radio, television being low energy. It makes sense if you think about it like that, but you also need to recognize that a longer wavelength means less energy. Shorter wavelength that means more energy. And the way I like to think about it is how many times am I hitting the surface, right? So just think about these waves crashing into a wall, right? If I have a long wavelength, then essentially the top of my crest is hitting very slowly, okay? But once I speed up those wavelengths like a gamma ray, then I'll just be slapping on it constantly, okay? So that's kind of how I think about energy. It's not perfect analogy, but yes, low wavelength equals high energy, all right? And visible light is a form of electromagnetic radiation. Two important points to keep up with. All right. So your video will also go into the electrons. Electrons are arranged in very particular ways called energy levels, and they add on a certain number at a time. So the first energy level has 2 electrons in it. Let me see, N equals 1. Here we are right here, this little stack of books. Okay, so the first energy level can only hold 2 electrons. All right, N equals 1. That means it can only have 2 electrons. And on the periodic table, actually, let me pull it this way. All right, these are arranged based on those electrons. Okay, so all of the ones in this column in group 1 will have one extra electron sitting around its shell. Okay, so that one is kind of telling you that it has one electron. This one will have 2 electrons. Skip over to the nonmetals, 3, 4, 5. Oxygen has 6 electrons on the outer shell, 7. And then noble gases have all 8 electrons with the exception of helium. Helium has 2, and that's what we said. It fills out that first level. N equals 1 can only have 2 electrons. So that's how come helium is here by itself. That's how come hydrogen is here by itself. This first level can only have these 2 electrons. Alright, and then the next level will go up to 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? So that's kind of how I keep track of it, right? The first energy level, 2 electrons. The second energy level can have 8 electrons. Can hold 8, but these elements don't, right? Because we just said this is how many electrons are on its outer shell, all right? So this way, it's the number of possible electrons, and then this way, it's how many there actually are, all right? That's how I think about it. So first row can have 2. This one only has 1. This one has 2 electrons. Second row can have up to 8, but this first one only has 1. Second one has 2. Third one has 3, 4, 5, so on. Okay? All right. Go back to your text. Let me swap this over for you. Boop. All right. And this is what we talked about with the wavelength, right? The longer the wavelength, the lower the energy. So that's important to remember. And this is where they'll talk about arrangement for the periodic table and for the atoms. That ought to be fine there. Okay, so it mentions valence electrons. I'm going to go back to that periodic table and show you, because we just talked about it a little, but I want to touch on it again. So a valence electron is the number of electrons on the outer shell. Okay, so when I start filling up these elements or these atoms with electrons, I'm going to fill them up one shell at a time. And we said that the first energy level can only take 2 in the shell. So I'll fill those up. First 1, then 2 will give me helium. Okay, now I have to move to the next shell. The next shell can hold 8 electrons. So I'll fill them in one at a time. After I add the first one, I have a total of 3 electrons, right? 1, 2, 3. But I only have 1 valence electron on the outer shell. So I filled my 2 in the first shell. Now I'm adding valence electrons to the second shell. N equals 2. So once I add 1 electron, I'll have lithium. I'll add 2, I'll make beryllium. 3 boron, 4 carbon, so on. So the valence electron is the number of atoms on the outer shell. And an easy way to think about that is with this group number, right? We said that earlier. If I have 4, if carbon is in group number 4, then I should have 4 valence electrons. And there'll be ways that a chemical equation can tell you whether or not it has more or less than the standard amount of electrons. Okay, so valence electron is the electron on the outer shell, all right? And the video goes into this. I'm going to have more. Let me know if you get confused about anything. Please ask questions. Like I said, I'm so used to being in person and being able to read your face and tell what you're getting, what you're not, how I can help. It's very difficult for me doing it this way. I don't know if I've covered everything. So let me know what you need help with, and we'll try to get something that works. All right, back to the book. Let's Somebody said I said I too much. I'm working on it. All right, so here's what we were just talking about, right? With the number of valence electrons. And these are drawn in what is called a Lewis dot structure. So I'm going to add a video for doing Lewis dot structure as well. It's going to be very helpful. And then when you count these dots, these are the number of valence electrons around the atom. So this will help you solve any problems that you'll have like that, being able to draw a Lewis dot structure. And then when you start combining atoms to make compounds or do chemical equations, Lewis dot structure will also be the easiest way for that. So get some practice in on that. Be very helpful going forward. We talked about the characteristics of different atoms, and that's just kind of what this is saying. Talks about metals. Metals have the ability to give up and accept valence electrons very easily, which is why they're so useful in combining, right? I combine metals to make steel or gold or brass, bronze, whatever, right? That's one of the reasons that it's so useful in that way. Carbon is also one of those, but it is organic chemistry and has much more depth to it. All right, that's chapter 4. Do some review if you want. I'm jumping right into chapter 5. We're just going to keep on rolling because it's all related. We just talked about this: mass number, atomic number. Radioactive elements or radioisotopes can have varying numbers of neutrons. Okay. Or protons, excuse me. The isotopes were neutrons. Radioisotopes are protons. Sorry about that. All right, so it kind of goes into what's going on. So it gives off a radioactive element, gives off these high energy particles. There's different kinds of them. There's beta particles, gamma rays, alpha particles, positrons, and they all have different levels of energy. It's not that important for this portion of the course, so I'd kind of look over it, but I don't necessarily think you need to like really know it in depth. Okay, so I'll add a nuclear chemistry and it'll mention all these, but as far as being able to do math with it or just basically I want you to be able to identify it, right? If I say I lose a proton, you know, am I a radioisotope or an isotope? You should be able to tell me. Basically, that kind of depth. All right. Let's see. Decay, right? We lose those particles over time. It'll mention fission, which is where an atom splits apart, creates a lot of energy. The nuclear bomb is essentially a fission experiment, and it ends up causing a chain reaction where the atoms will explode. Those atoms will hit something else, cause them to explode, so on and so forth until everything is radioactive, essentially. All right, let's see. I think that'll be good for now. You may have a half-life problem on there. It's pretty straightforward. So, maybe. I don't know. I'll look on there and see what the problems look like. But I didn't do much half-life when I was coming through school. It is an important concept to know. So half-life is the amount of time it takes for 1/2 of a sample to decay. So if I have a radioactive element, let's say uranium, right? And I say the half-life of this element is, or this isotope is 1,000 years. That means it'll take 1,000 years for half of that radioactive material to decay, to go away. All right, so then another 1,000 for half of that to go away, and it ends up becoming an exponential decay over time. And that's why we put a lot of our radioactive materials into concrete blocks that essentially will last forever. Sit them in the bottom of the ocean. We hope we contain the radioactive material within that concrete slab, because it's going to be putting off radioactive material for thousands of years. All right, based on the half-life. That's what the half-life tells us. How long will that thing be radioactive? All right, pretty straightforward there. Medical applications, good. This is what we were talking about with the fission and the chain reaction, nuclear chemistry. Okay, I think that will be good for today. We'll get in ions tomorrow because that'll be part of your lab. We're going to do some rearranging and do some chemical equations. So big day tomorrow. Look over your videos, maybe get started on your master in chemistry. And like I said, no lab today. Keep up the good work. I'll see y'all tomorrow.